Discussion of similarity in section 222. Today you will focus on the relationship between the lengths of the sides of dilations by enlarging and reducing polygons and looking for patterns. We already talked about this a little bit in 221. We should have a common scale factor if we're going to have similarity. And that scale factor is just a fancy way of saying a multiplier. So you will then learn what it means for two polygons to be similar. So for your work from problem 251, the shapes that you created should resemble those at the right. Although I don't remember, I don't think it went through origin, so not exactly, but whatever. Anyways, in problem 251, you dilated ABC by a factor of 2, imagining, oh wait, that's probably a homework problem, huh? 251 is probably a homework problem, my mistake. So anyways, in 251, you dilated ABC by a factor of 2, imagining two rubber bands to create A prime, B prime, C prime. Which side of A prime, B prime, C prime responds to CB? Well, CB is right here, so I would say B prime, C prime probably does. So here I will say C prime, B prime. I could also call it B prime, C prime. It doesn't matter if you go B prime, C prime or C prime, B prime. It's the same. Which one corresponds to AB? Well, I would say A prime, B prime does. So hopefully we're all on board with those. On A. So B, it says, what's the relationship of the corresponding sides? Write down all of your observations. How could you determine the side lengths of A prime, B prime, C prime from the side lengths of ABC? Well, here's one thing I noticed. I noticed these lines are the parallel, or actually the same line, right? Well, the same line is parallel to itself. These lines are parallel. So BC is parallel to B prime, C prime. AC is definitely parallel to A prime, C prime because it's the same line, right? And the same is true for AB and A prime, B prime. So I definitely have parallel lines. The other thing I would say is that the side lengths look double, right? From AC is 3 and BC is 4. I know that this is a right triangle, so it's a very famous right triangle is 3, 4, 5. Well, I'll change the colors here, and I will say A prime, C prime is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 for B prime, C prime. And I'm guessing, hey, look, 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. So 6 squared plus 8 squared should equal 10 squared. Obviously doing the Pythagorean theorem because this is a right triangle. So the leg squared plus the leg squared should equal the hypotenuse squared. And then I'll go back to black for the small one. It's going to be 3 squared plus 4 squared is equal to 5 squared, right? That's how I knew that that was 5. So hopefully you know those 3, 4, 5 triangles, super famous. If you didn't, there you go. So anyways, what relationship do the corresponding sides have? Well, I would say they are parallel and have a common scale factor. And again, a scale factor is just a fancy way of saying a multiplier. So in this example, the scale factor would be 2. All right, so why does A prime, B prime lie on AB and A prime, C prime lie on AC, but B prime, C prime doesn't lie on BC? So essentially, let me go ahead and kind of clear this off here. Here's what they're saying. How come this line goes through origin and this line goes through origin, but these lines don't? And the answer to that would be, I think, the point of dilation, right? This line is on the point of dilation, so it just keeps going. This line is on the point of dilation, so it just keeps going. This line is not on the point of dilation, so it doesn't just keep going through. So that's why, so it's a happy mess right there. That's why this line goes through origin, and this line goes through origin because it's on, but this one isn't. So I hope that makes sense, and we're all okay with that. So I could say, again, line BC is not on the point of dilation. Sorry, I got a little lost in my thoughts there. So could you determine the side lengths of A prime, B prime, C prime by adding the same amount to each side? No, I would say no, you definitely couldn't. So here's what they're saying on that. What they're saying is that to get from from AB to A prime, B prime, right? I went from 3 to 6. So I actually had to add 3. Well, to get from BC, which was 4, to B prime, C prime, which was 8, I actually had to add 4. So what they're saying is, could I just keep adding 3, right? And go, like, this was a 3, 4, 5 triangle. Can I just add 3 and go 6, 7, 8? Because I added 3 each way. And of course the answer is no, because it was 6, 8, 10. So it's a multiplier. It's not an adder. So I would say no. No, we're not adding to the sides. We're multiplying by a common factor. Again, I don't want to leave the impression here that we're adding. This is definitely multiplying. So it says Monica dilated ABC to get a different triangle. She knows that AB is 20 units long. So let's take a look at what she did there. She knows that AB... what's going on here? I kind of lose the... Oh, I know what I'm doing. Okay. I forgot if you kind of go off, then you lose the ability to erase. All right. So what we're saying here is that this was 5, and then this one ended up being 20. Well, what's your scale factor there? So it's going to be 5 times the scale factor is going to equal 20. So hopefully we all see the scale factor is obviously 4, right? So we're going to multiply by 4. So how many times longer is AB is A double prime, B double prime? And how long is B? I would say, so this is going to be 4 times bigger because that's our scale factor. So how long is B double prime, C double prime? Well, this is 1, 2, 3, 4 already. And we're just going to multiply 4 by 4, so we're going to get 16, right? So this one out here, this B double prime, C double prime, is actually going to be 16 because we're multiplying by 4. So hopefully we see what's going on there. I feel like I've been as clear as mud. So it says Casey decided to dilate her favorite letter, C, of course. Clever. She dilated C using a copy machine. The scale factor, or zoom, that's how much it's going up or down, tells the copier how much to dilate the figures or text on the paper. So for example, if Casey sets the zoom on 200%, that's the same as the scale factor of 2. And hopefully we know 200% equals 2, right? You just move the decimal 2 places. 200% becomes 2. So I hope we're okay with moving that. It says the side lengths would be doubled. If she sets it at 50%, again, we would move it 2, and her scale factor would be 0.5. So it's just turning a percent into a decimal is all we're doing. The machine would shrink the side lengths in half. So zoom is often written as a percent, while scale factor is usually written as a decimal or a fraction. So if you're using a copy machine, expect to see those percents. If we're doing math, expect to see a decimal or a fraction. We're going to be doing a lot of this and not so many percents. So the copier does not change any of the angle measures, therefore the copier is dilating the figure. So it says Casey wants to learn more about her dilated C's. Since the scale factor multiplies each side of the original polygon, then the ratio of the widths must equal the ratio of the heights. What we're saying is this ratio, 8 to 24, would have to be the same as this ratio of 6 to 18. Everything is going to be proportional. It needs to be proportional, otherwise we don't have similarity. So it says Casey decided how to show these ratios in the diagram are right. Verify that her ratios are equal. Well, so what she's saying is that the big C, right, height, the big height divided by the small height is 24 over 8. So she should put the big width over the small width of 18 to 6. So that makes sense. So it says verify that her ratios are correct. Well, 24 divided by 8 is 3, and 18 divided by 6 is 3. So she has that same scale factor, that same ratio, so I think she did a good job. A proportion is an equation with two equivalent ratios. So after looking at Casey's work, her brother wrote the proportions as 8/6 compared to 24/18. Are his ratios in fact equal? Well, he's not comparing the big triangle to the big C to the small c. What he's comparing is the height of one c to the width of that c, and the height of the other c to the width of the other c. And yeah, I mean, I think 8/6 is 1.25, and 24/18, actually, I lied to you. It's 1.3 repeating. I apologize. If you grab a calculator and divide 8 by 6, you'll get 1.3 repeating. And 24 divided by 18 was also 1.3 repeating. So yeah, that actually seems to work as well. How could he show his work on the diagram, copy his diagram, right? So I think the point the book is trying to make here is that there needs to be a relationship from one C to the other, but there also needs to be a relationship in the parts of the small c to the parts of the big C. You just can't get it twisted around as backwards. So and let me kind of see if I can make sense of this, because the book is kind of throwing a lot at us right now. So what we're saying is this. We can make a couple of different comparisons here. In this example, we can compare 8 to 24. Actually, I guess they did 24 to 8, so I should probably do 24 to 8. They can compare 24 to 8. But if we do, we went the big to the small, so we need to go the big to the small. And that's okay. Or we can compare the 8 to 6. We'll compare the small c to itself. That's the same as 24 to 18. And that's okay. We could compare the big width to the big height, as long as we compare the small width to the small height. And that's okay. All these work out fine. This is going to give me 0.75 and 0.75. But what we cannot do is say, all right, I'm going to compare this 8 to this 24. So I'm going to compare the height to the height, and I'm going to start with the small to the big, and then I'm going to compare the big back to the small, right? So here I have the small one, the small c, and the big C, but then I switched it and put the big C and the small c. There's no consistency on that. That is not okay. So there's a bunch of different ways to do this correctly. There's multiple ways to do it incorrectly, but you just have to make sure that you're setting it all up. And I think I've made this probably more difficult than it needs to be. So I'm going to wrap this up by saying the following. Here's how I like to do it, just so that I know that I'm consistent. I'm going to take a part of the small and compare it to the same part of the big. So essentially I have the small one over here and the big one over here. Then I'm going to compare the small other part that I didn't compare to the big other part that I didn't compare. And I should be fine. And if I'm not sure, I can cross multiply. 8 times 18 is 128. 124. I take that back. And it's 144. I take it back even more. 8 times 18 is 144. And 24 times 6 is 144. So if I cross multiply those, I should get the same answer. So it doesn't really matter how you set your ratio up. As long as you cross multiply and get the same ratio, you should be fine. I'm going to pause for a second and rethink my life. Completely confused you by now. I'm very sorry, but now we're going to do some examples with real numbers, so hopefully we get a little bit of clarity to what it is that I was talking about. So it says Casey decided to create an enlarged C for the door of her bedroom. To fit, it needs to be 72 inches wide. So she already knows how wide she wants it to be. She just doesn't know how tall she needs it to be, and she already has the ratio. So there's a couple different ways that she can write this ratio out and solve it. It says if x is the height of the C, write and solve an equation to determine how tall the C is on the door. Be ready to share your equation and solution with the class. So a couple different ways that we can do this. One way we can do this is we can say, all right, well, I know that I'm going to set this thing up, and I'm going to go ahead and I'm just going to say 8, or this 6, I'm going to go again small on top and big on bottom. So the small 6 goes with the small 72, or the big 72. So the small 8 has to go with the unknown. And now I have that set up. I can cross multiply. I'm going to get 6x. I'm going to grab my calculator here because it's going to be a big number. I'm going to get 72 times 8 is equal to 576. So I'll go back over here. It's equal to 576. I'll divide both sides by 6. And x is going to equal 96. So I know that this needs to equal 96. Now, some of you might have thought, well, geez, Oliver, the scale factor here is pretty obvious. I know I'm just going to multiply 6 times 12 to get 72, so I guess I just need to multiply 8 by 12 as well. And 8 times 12 is also 96. So that's fine. You can do it with the proportions and setting up the fractions, or you can just do it by raw computing power and realizing what the scale factor is. It doesn't matter to me. What does matter is that you have the same scale factor or that your proportions are equal. That's what's so important about this. So Casey wanted to make a reduced C to wear on a necklace. She has decided she would like the height of the C to be 2. So let's go ahead and make another C for her here. And we'll go ahead and, that didn't go well for me. We'll do this instead. Okay, so we have one C that looks like this. This is the original C, but now she's going to make a smaller C, and she needs the height to be 2, and we don't know how wide it needs to be. So let's figure this out for her. Well, I'm guessing some of you already see a shortcut, but let's go ahead and set up the ratio. I'm going to do the original on top and the new one on bottom. So my original 8 goes to this 2, and the 6 goes to, I don't know what, so I'll cross multiply. I get 8x equals 12. I divide by 8, so x equals 1.5. And that's probably not a surprise to some of you guys that already realize that you could say, well, look, I'm just going to divide this one by 4. 8 divided by 4 is 2, so now if I divide 6 by 4, I don't know what I was thinking right there. I'll just divide 6 by 4. I'm going to get 1.5. Some of you might have went in the opposite direction. You said, oh, look, 2 times 4 is 8. What times 4 is 6.5? I'm sorry, what times 4 is 6? Obviously, that would be 1.5. So either way, we need that width to be 1.5. Again, I'm going to pause and rethink my life. There's a lot going on with this video. It's way too long already. All right, so now what would happen if the scale factor between Casey's C's was equal to 1? Well, let's see here. 8 and 6. I'm going to multiply this by 1. I get 8. 6 times 1 is 6. It would stay the same size, right? Same size, which hopefully we remember means congruent. It would actually stay congruent. All right, I'm going to pause and set up the final section. Rashida drew triangle ABC at right and then dilated through point A to create A prime, B prime, C prime. So first she had the big triangle, then she sort of cut it in half. All the lengths are in centimeters. So why are the two triangles similar? Well, we know they're similar because of angle similarity, right? We know here that we have, actually, yeah, we have angle similarity. It's just the same thing cut in half if these lines are parallel. So it says write a triangle similarity statement. So I will say triangle ABC is similar to triangle A prime, B and B matchup, B and B prime matchup, and C and C prime matchup. So A goes with A prime, B goes with B prime, C goes with C prime. It says Rashida then decided to redraw the diagram as two separate triangles, and I'm going to tell you right now, this I think is a big deal. Whenever you see these overlapping triangles in years past, students always get really confused, and so I would always kind of tell you guys to break these things apart, and what you're going to see here is kind of interesting. We know that the small side is 4. We don't know what this is. We know this is x. So if this here is 6, well, hopefully it makes sense that we have to add 4 to that. That's how we get a 10. And if this side right here is 9, well, we have to add x to that. That's why we're going to get x plus 9. I know a lot of times kids get confused here because instead of putting a 10 here, they'll put a 6 here just because they see the 6. But remember, 6 only goes this far. You have to add 4 to it to get your 10. And again, same thing. 9 only goes this far. You have to add your x to it to get your x plus 9. So I hope that makes sense. It's just a tricky little thing that a lot of kids seem to miss over the years. That didn't go the way I wanted it to. Let's cancel out of that and keep going here. All right. So it says Rashida then decided to redraw the triangle as shown, write the proportion, and solve for x using the corresponding side. So what I'll do is I'll say, well, I know that I'll start with this one. I'll have the small one on top and the big one on bottom. And again, I think it's real important to have this ordered in. It doesn't have to be this order, but it has to be an order that makes sense. So I'm going to go the small one, which is 4, and I know that 4 goes with the 10. To the big one, that's 10. This x corresponds to this x plus 9. And I know this looks really complicated, but it's really pretty simple. This just means I'm going to multiply 10 times x, and I'm going to compare it to 4 times x plus 9. Right? I'm going to multiply the bottom here times the top here, and cross multiply it times the top here and the bottom here. I'm going to get 10x equals 4x plus 36. Subtract 4x. I get 6x equals 36. Divide by 6. X equals 6. Let's see if this makes sense. That would make this 15 and this 6. So 4 times 2.5 equals 10, and 6 times 2.5 does indeed equal 15. You can verify that with a calculator if you want. So I feel pretty good about all that. So it says how long is AC? AC ended up being 15. I'm sorry, AC. AC is 15. AC prime is 6. What is the ratio of the original segment BC to the original segment B prime C prime? So what we're going to say is this, that we know that B prime C prime is smaller, so B prime C prime times 2.5 equals BC, right? That's going to be how we do that. Or if we work backwards, BC divided by 2.5 equals B prime C prime. It just depends if you're going from small to big or big to small. What's the relationship between B prime C prime and BC in the original diagram? It sure looks like, and this is going to be important later, but not right now, these are parallel lines, right? So we have some parallel lines there. I think this might be the longest video ever. All right, so after seeing Casey enlarge the C, Al had an idea. He drew the 60-degree angle as shown in diagram 1 at right. He then extended the sides so that they're twice as long. So let's say the sides here, we're just going to pretend, let's say that this was x and this was y. Well, this would be 2x and this would be 2y. And what he's saying is, hey, look, I doubled this, so therefore the new angle must be doubled as well. It must be 120 degrees. Would you agree or disagree? I would strongly disagree, right? Hopefully we know this is also going to be 60 degrees. So the idea is going to be this. The shape stays the same, which is the angles, right? So the shape stays the same, so the angles stay the same. But the size changes. Therefore, the sides would double. Okay, but the angle would stay the same. I apologize for this. There's again some more dilation stuff that we did in lesson 221. I'm finally ending this video. Have a good one.